Welcome to our summary of Chapter 2, where we talked about modular arithmetic. Now, just a reminder, when I say chapter, it is a chapter in an imaginary book. I am really just using the chapters to break down the sections of what I'm talking about, which roughly are intended to correspond to weeks, but I'm just going to let the chapter breaks fall where they may, just to break up the material for you in a coherent way. So, to start with, let's remember that modular arithmetic really has two fundamental views towards what it is. The first view is that what modular arithmetic is really about is remainders. So when someone asks the question, hey, what's 13 mod 5? And you say, it's 3, you're really answering the question, what's the remainder when you divide 13 by 5? And the answer is 3. And the way this would be written in some sort of programming language, for example, would usually be this, with this percentage sign. And this percentage sign here is a mod operator. It's giving you the R from the division algorithm. By and large, when computer scientists talk about modular arithmetic, they probably are thinking about it this way. So when they ask, for example, what's 2 plus 3 mod 5, and they say, oh, it's 0, they're really thinking about this interpretation. They're just mentally shoving this percentage sign at the end, and then giving you the result. Now, if you think about the world in this view, well, there's only a few remainders mod 5, because remember, the remainder from the division algorithm is always one of 0, 1, 2, up to whatever you're dividing by. And so in this case, it would be anywhere from 0 up to 4, because I'm dividing by 5. So from this point of view, people might be inclined to tell you, okay, well, there's no such thing as a 7 in the mod 5 universe. But that's kind of an unhelpful view because, well, I know what 7 is, so I would like to be able to talk about 7 even when I'm working mod 5. And so if I want to be able to do that, then I really want to think about it from the other point of view, which is the equivalence class view. Here, instead of being a single number that you get when you divide something by something, each number represents an entire class of numbers with that remainder. So if you recall when we talked about the division algorithm, I called these things buckets. What is really happening in this view here is that each number is being used as a stand-in for its entire bucket. So when I think about 7 mod 5 in this point of view, I'm really associating the number 7 not with just 2, but with the entire set of things that looks like this. So 7 is standing in for this entire infinite set. So from this point of view, when someone says, what's 3 times 4 mod 10? It might be acceptable to give the seemingly kind of cheeky answer 12. Because this is a perfectly true statement. But again, note, 12 is in this set, so is 2. So when I'm thinking in the mod 10 universe, and I'm thinking about it from this point of view, what I'm really trying to think of is 12 and 2 are the same number. Now, these two views are quite compatible, but they're a little bit different, and a lot of times when you hear people talk about this, they'll sort of freely flip-flop between these two points of view without sort of like clearly articulating which of these two things they're really thinking about, or if they're sort of freely switching back and forth. Computers are almost always going to think about it in this regard, because, well, a computer is not going to be thinking about a set, because a computer is not really thinking about anything. However, a computer can run the division algorithm, and so a computer can always spit this out. And so when we talk about how things are working algorithmically, even if mentally we're thinking about it from this point of view, the computer is going to be doing this. And so we're going to need to freely switch back and forth between these whenever we're going to talk about doing actual computations. The way I encourage you to think about this overall is that modular arithmetic creates for each number n its own number system. So in the same way that you've been thinking about the real numbers as your number system for a really long time, and then maybe someone came along and said, oh, well, you could think about the complex numbers too, or maybe they went the other way and said, oh, well, you could just think about the rational numbers. In the same way, every n gives you a different number system. So I'm not just giving you one new number system, I'm giving you infinitely many new number systems. So the mod 2 number system, the mod 3 number system, the mod 4 number system, and so on and so forth. And each of these number systems has its own operations and its own properties. Now, an important thing to note here is that regardless of which of these two views you take, there are only n things mod n. In one case, those n things are n of these giant sets, and in the other, it's the numbers 0 through n minus 1. But in both cases, if I think how many things are there mod 7, well, there's 7. And this is one of the very nice properties about the mod n number systems, is that because they are finite, we can understand them completely, as in you could write out every possible sum, product, whatever you want. This is in, of course, sharp contrast to even something like the integers themselves, which are certainly infinite. And so as much as you might say, I understand integer addition, you understand integer addition in the sense that you could add any two integers that you were given, but you don't understand it in the sense that you've literally written down every possible sum of integers because, well, there's infinitely many possible sums of integers. There are only finitely many possible sums mod any particular n. Now, I mentioned that each of these number systems comes with its own operations, and I already mentioned that two of those operations that you get are addition and multiplication. And these operations you get always. Along with addition and multiplication, you also always get subtraction, and we also get exponentiation. But keep in mind, when we raise something to an exponent, and we're talking about it mod n, I can interpret the a mod n, but the b here is not a mod n thing. The b here is actually a positive integer. And so, for example, what does a to the 17th mean? Well, it literally just means a times a times a times a times a 17 times. And so this exponentiation here is really something that is only being used to specify repeated multiplication. So we have all of these operations, no matter what two elements you pick. If you want to subtract two things, mod n, you go right ahead, you can do it. If you want to raise a thing mod n to a positive integer power, you go right ahead, you can do it. Just like the real numbers, though, there's some operations that aren't always going to work. So for example, you cannot, in fact, divide all pairs of real numbers. For example, you cannot divide 3 by 0. As we talked about, we're going to prefer to think about this as inverses. So rather than thinking about a divided by b, because that's a little messy, we're going to tend to think about a divided by b as just being a way of representing a times b inverse. And then when we talk about what b inverse is, well, b inverse is the thing that you multiply b by in order to get 1. And so this is something that we've talked a lot about, and I'll summarize the result in a minute, but you don't always get to divide by things. And in particular, you often even don't get to divide by things that aren't 0. Sometimes there are other things you can't divide by. Again, like the real numbers, there is a square root function, or a cube root function, or a fourth root function, or whatever you want. But again, just like the real numbers, it might not always be defined. For example, if you try and take the square root of minus 4, it doesn't work. You don't find a real number whose square root is minus 4. If you try and take the square root of 9, though, you actually find two things. You find plus 3 and minus 3. And so we'll see often it works the same way in mod n land, where sometimes you'll take a square root and you'll find out, hey, this is just a thing that doesn't have a square root, and sometimes it'll have two square roots, and sometimes we've actually seen it'll even have more than two square roots, which is something that never happens with the real numbers. Another sometimes operation is the logarithm. Again, with real numbers, if I took, say, the natural log, I'm only allowed to take the natural log of numbers that are positive, not numbers that are 0 or negative. Likewise, when I go to calculate logarithms in the modular universe, I'm going to find that sometimes they exist and sometimes they don't. And we've talked a little bit about when they do and when they don't and that kind of thing. But again, these are sometimes operations that again behave a lot like the real numbers. All of these things that are only sometimes defined mod n, they're also only sometimes defined in the real numbers. Our biggest theorem this week is this theorem on inverses, which says if a is an integer, then a has an inverse in the mod n world if and only if the greatest common divisor of a and n is 1. Or another way to say that is if and only if a and n are relatively prime. Now, as an example here, let's write down the numbers mod 15. So there are 15 numbers, mod 15. They are these. And so let's think to ourselves, which of these things have inverses? It should be the ones that are relatively prime to 15. 0 is not relatively prime to anything but 1, so it's definitely not relatively prime to 15. 3 shares a common factor of 3. 5 shares a common factor of 5. 6 shares a common factor of 3. 9 shares a common factor of 3. 10 shares a common factor of 5. 12 shares a common factor of 3. So the things that will have inverses are 1, 2, 4, 7, 8, 11, 13, and 14. I'll remind you that we went ahead and gave a name to the number of things that have inverses, or the number of things mod n that are relatively prime to n. We called that the Euler phi function, and so we just calculated that phi of 15 here is 8. Again, this will be a key role player later in the course. So let's write down what each of these inverses are. So one inverse is always going to be 1, and that's because 1 times 1 is 1. When I go to think about 2 inverse, I'm asking the question, what do I have to multiply 2 by in order to get 1 mod 15? And I don't think it's so tricky to figure out that the thing I have to multiply 2 by is 8. 2 times 8 is 16, which is 1 mod 15. Now, remembering that being an inverse is mutual, the fact that the inverse of 2 is 8 also tells me that the inverse of 8 is 2, so I'm going to go ahead and write that in right away so that I don't forget, and so that I don't recalculate this. 4. What's the inverse of 4 going to be, mod 15? Well, this is a little bit odd, and you might go ahead and try everything else and be like, wait, does it not have one? Isn't it supposed to have one? And 4 does have an inverse mod 15, but weirdly enough, the inverse of 4 mod 15 is 4. That being, again, because 4 times 4 is 16, and 16 is 1 mod 15. Okay, so next up, what's the inverse of 7 going to be? Now, this one might take you a bit, but when you're doing this, what you're really doing is you're going through the list of multiples of 7, and what am I looking for? I'm looking for one of these multiples that is 1 more than a multiple of 15. And it would help an enormous amount if I wrote down the multiples of 7 correctly. Now, presumably you didn't make 16 errors trying to add multiples of 7 like I did, but 91 is the number I'm looking for. Why? Because 91 is 1 more than a multiple of 15, namely 90, which is 15 times 6. So 91 is the first number of the numbers on this list that is 1 mod 15, which means that in fact the inverse of 7 is 13. And so you might remember that 91 is this annoying number that looks prime but is actually 7 times 13. There that shows up again. And also, while we're at it, the inverse of 13 then is 7. Now, I want to point out that was kind of messy. But, as usual, if we're willing to think a bit more and use all the tricks we have at our disposal, this is actually much easier. Namely, what is 7 mod 15? Well, 7 mod 15 is minus 8. Well, why is that? Because 7 plus 8 is 15. And so what that means is 7 inverse is the same as minus 8 inverse, which is going to be minus 1 inverse times 8 inverse. And I'm just writing this out slowly so you can see everything that's happening here. minus 1 inverse. Well, actually, minus 1, remember, is 14. But remember, minus 1 is always going to be its own inverse, and that's because minus 1 times minus 1 is always 1. So that we know is its own inverse. So this is going to be a minus 1 times, and then the inverse of 8. But while the inverse of 7 was painful, the inverse of 8 we actually got right away. It's 2. And so then we get that 7 inverse is minus 2, which, lo and behold, is 13. Now, how do I know all of that worked? And the reason why I know that stuff worked is that I can do all of these operations in the integers, and only after I have thought about them in the integers, where I know all of this kind of chicanery is fine, can I go back and reinterpret things mod 15. Here I'm really making heavy use of the fact that any number mod 15 is not just the number, going back to our second viewpoint. It's also a stand-in for all of the other numbers that have the same remainder when you divide by 15. And so, if you would rather work with a minus 8 than a plus 7, as happened to be in this case, you're certainly welcome to replace 7 with minus 8, because, again, mod 15, they're literally the same number. Okay, so what's 11 inverse? Now, you can think through all the multiples of 11, and wait until you find one that's one more than a multiple of 15. You could also try this minus trick. But actually, there's something you can do which is even easier, which is to note I have filled in the inverse of literally every number except 11. And remember, being an inverse is mutual. And so what that means is there's only one number whose inverse could possibly be 11, namely 11. If the inverse of 11 were anything else, the inverse of that something else would be 11, but none of these things had an inverse of 11. Now, again, if you think that sounds kind of fishy, maybe I don't believe you, then you can check 11 times 11 is 121, which is one more than 120, and 120 is definitely a multiple of 15. So this is definitely correct. And so these are all 8 numbers mod 15 that have an inverse, and what their inverse is. And you can expect that on some future quiz I'll give you some small number like 15, where I will ask you to do this same thing. Cross out all the ones that don't have an inverse, and then write down what the inverse is of each of them. This is something that we can handle. Now, that was all just by guess and check, but of course we talked about how to actually calculate the inverses if you're working mod a larger number where guess and check is not going to do it. So if you wanted, for example, to find, say, 13 inverse mod a 100-digit number, you definitely don't want to do guess and check to do that. Rather, what we've seen is that the extended Euclidean algorithm, with no modification, already calculates the inverse. And, in fact, the extended Euclidean algorithm does even better, because it also calculates whether the number has an inverse. Why is that? Because what the extended Euclidean algorithm does is it first calculates the GCD of two numbers a and, let's say, n, just so that we can call the modulus n still. If this GCD it calculates is not 1, well, then a and n aren't relatively prime. A doesn't have an inverse, mod n. Cross out the number. If, on the other hand, d is 1, remember the extended Euclidean algorithm additionally gives us these numbers x and y, such that ax plus ny is equal to d. But remember, d here is 1, because if d was anything other than 1, the number just doesn't have an inverse. But the key thing is, if I look at this equation, mod n, well, this just is a multiple of n, so it just disappears, and so I get that ax is congruent to 1 mod n. And so, in other words, x is the inverse of a. So, in particular, the thing the extended Euclidean algorithm does that the Euclidean algorithm doesn't is calculate these appropriate x and y, and one of those works out to be the inverse of a mod n. Note, it will only be x if x is the coefficient of a, It might be that x is the coefficient of n, in which case y is the coefficient of a, and then y is a inverse, however you happen to label your variables. So for every n, we get a mod n number system. But those number systems are not all equally nice. And so here when I use the word nice, what I really mean is more like the real numbers. So more like the kind of algebra and calculations that we're used to. So really there's sort of a spectrum for how nice this thing is going to be, where on the one end of the spectrum, the nicest end, we have that n is prime. If you can't have n prime, the next nicest thing is n being a prime power. And I'll go ahead here and note that for reasons that we may or may not get into later, powers of 2 are worse than powers of not 2. If you have to pick a prime power and you can avoid a power of 2, even better. And by the way, prime power, I just mean it is a power of a prime. So 49, for example, would be a prime power that is not prime. And then what's the last case is other composite numbers. So this is the least nice side of the scale. So for purposes of this week, we have mostly focused on the nice things that happen over here. We're going to save the intricacies of talking about composite moduli for a little bit later when we'll need them for various cryptosystems like RSA. But for now, I want to review what are the nice things that happen when we work with a prime modulus. So here I'm going to call my modulus p, just to remind me that it's prime. And I'm going to write down here the theorems we've talked about that are only true for prime moduli. And my goal here is to try and sort of again remind you the ways in which these theorems resemble the things about the real numbers to the extent that they do. So the first thing that's really nice about prime moduli that's true only for prime moduli, and that follows immediately from our discussion of inverses, is that when I'm working modulo a prime, every non-zero element has a multiplicative inverse. This is because no non-zero number can have a GCD with p that's something other than 1, because if a remainder mod p has a non-trivial GCD with p, that means that p has a factor, which means it's not prime. So every non-zero element automatically has a multiplicative inverse. Which, again, is exactly like the real numbers, where you can divide any two real numbers as long as the number you're dividing by isn't 0. In the fancy lingo, an algebraist would say this makes the integers mod a prime a field. Now, another thing we talked about that works a lot like the real numbers is square roots. So modulo a prime, it is true that 0 has one square root, namely 0, because 0 squared is 0. And then exactly half of the remaining elements, again here p not 2, we'll say, exactly half of the remaining elements have 2 square roots, and the other half have 0 square roots. Again, this is very broadly like the real numbers, where if you think about it, 0's only square root is 0, and then all of the negative real numbers have no square root. And all of the positive real numbers have 2 square roots, one positive and one negative. Here it's not quite so easy to see which elements have a square root and which ones don't. So let's say I worked mod 101, for example. Well, 0 has one square root. But then I know that 50 elements have no square root at all. That's half of the 100 non-zero elements. And then 50 elements have 2 square roots. And your 2 square roots will always come in a pair of plus minus something. So if one of your square roots is 3, for example, 9, if you look at the square root of 9 mod 101, one of the square roots is 3, and the other is 98. It always happens in these plus minus pairs. But whereas with the real numbers, if I gave you a real number and asked, does it have 0 square roots or 2 square roots, you could immediately tell me. So for example, negative 18, you could probably immediately tell me 0 square roots. 179, you could immediately tell me 2 square roots, because it's really just the question of, is it positive or is it negative? It is not super clear if I show you a number like 101. Is 2 a square mod 101? That is, Does 2 have 2 square roots mod 101? Or does 2 have 0 square roots mod 101? What about 3? What about 4? What about 5? Now, one of those you should have been able to answer. Namely, you should know immediately that 4 has a square root mod 101, because you can immediately think of a square root of 4 mod 101. Namely, 2 is definitely a square root of 4 mod 101. Likewise, so is 99, which is minus 2. Now, just in case you're curious, I'll go ahead and tell you for the first few of these. So, 2 does not have a square root mod 101. 3 does not have a square root. Of course, 4 does. 5 actually has a square root. Namely, you can check that the square root of 5 mod 101 is actually plus or minus 45. By the way, I'm not doing this by hand, I'm just doing this by computer just to show you how this ends up working out. If you then look, 6 in fact has a square root. And I will leave it to you to check that that square root is plus or minus 39. Again, all I'm saying with this statement is that 39 squared mod 101 is 6. And that's something that's relatively easy for you to check. So, really, the squares and unsquares mod a prime are quite mixed up. But like the real numbers, it's sort of a 50-50 thing. It will take a little while for us to get to a point where we'll be able to rapidly identify what numbers are squares and what numbers are not squares. We will eventually learn how to do that, though. Just as a note, what happens that breaks this mod other numbers? What happens mod composites is that sometimes way less than half of numbers have a square root. And when that happens, you can convince yourself it also happens that some numbers have lots of square roots. So for example, even mod 8, you can check that the number 1 actually has 4 different square roots instead of the 2 you would expect. And so when you look mod composite numbers or even prime powers, you find that less than half of the elements have a square root, and then some of them have more square roots. So take whatever a you like, and then we can define this exponentiation function, f of x equals a to the x. Note a here has to be something mod p. A can't be like e, because there is no e mod p. But take any number mod p that you like, and then look at the function where I raise this to a power. And so, for example, I could take p here to be 13, a to be 3, and I am claiming here that if I write down this function, where I have here x, here a to the x, I guess I'll write it as 3 to the x. 3 to the first is 3, 3 to the second is 9, 3 to the third is 27, which is 1. And now this 1 tells me that now things are going to repeat. Because when I write down 3 to the fourth, it's now going to be 3. And then from 3, it'll be 9, 1, 3, 9, 1, 3, 9, 1. And so this will repeat 3, 9, 1, 3, 9, 1, 3, 9, 1 forever. The reason for this is simply that 3 to the fourth is 3 cubed times 3. So while you could do this as 81 mod 13, and then you have to think about it, okay, what is the multiple of 13 that's just less than 81? Then you get to, okay, 78, I guess, is 6 times 13. Yeah, that sounds right. And so that means, yeah, just like he said, 3 to the fourth is 3 mod 13. You definitely do not have to do that much work, because all I have to do is actually multiply the previous entry by 3. So 1 times 3 is 3. 3 times 3 is 9. 9 times 3, we already showed, is 1. And that's why this loops through this. And so just like a sine wave, or whatever other periodic function you have in mind, this function is just going to keep repeating on a loop forever. 391, 391, 391, 391. Okay, and so in this case, the period is 3. And sometimes you will hear the period of this function that you get out of the number a. You'll sometimes hear this called the order. So my claim was that the period would always end up dividing p minus 1. So in this case, p minus 1 is 12, and I ended up getting a period of 3. 3 definitely divides 12. Now, in fact, actually, whether the modulus is prime or not, the exponentiation function is always going to at least eventually become periodic. That is to say, it might do something weird at first, like it at first does something like, and then settles down into a periodic bit. But the thing that's definitely not true if you're not working modulo a prime is this fact that the period divides p minus 1. This is something very specific to primes, and in fact, it's something so specific to primes that we're actually going to use this later to help us identify numbers that are and are not prime. Just as a second example, I could have taken a is 2, in which case then my table would have looked a little bit different. So I'll write down 2 to the x, so that will go 2, 4, 8, 16, which is 3, 6, 12, 24, which is 11, 22, which is 9, 18, which is 5, 2 times 10 is 20, which mod 13 is 7, and times 2, 14, which is 1. And then the point here is, again, once I hit 1, and it is always when I hit 1 that this happens, as soon as I hit 1, I'm now going to multiply 1 by 2, which is going to give me 2, which I'm going to multiply by 2, which is going to give me 4, which I'm going to multiply by 2, is going to give me 8, 3, 6, 12, 11, 9, 5, ... Okay, and so this is going to be on a loop for all time. Here, the period also divides 12, but in fact, in this case, the period actually is 12. And so what you can see here is actually different A's have different periods. So you can see 3 had this period that was pretty small, but then 2 had this period that was as large as it could possibly be, because 12 is the largest divisor of 13 minus 1. This statement about periodicity has a common way of stating it that's a little bit different than what I've been doing here, but it's closely connected. Namely, notice what happens right before the repeat. Always, right before the repeat, I have to hit 1. And in fact, actually, if I hit 1 at 3, then I'm also going to hit 1 at 6, and at 9, and at 12. And so, in fact, actually, a different way to interpret this same phenomenon is that, in fact, a to the 12th is always 1 mod 13. As long as you're not in one sort of silly case, which is a being 0. If a is 0, then this function is just 0, 0, 0, 0, 0, 0, and then it's periodic of period 1, but it's not very interesting. Or, in general, so as long as p is prime, it's always going to be the case that if you take a non-zero number and raise it to the p minus first power, you will always get 1. And if you think about it, this fact is really what's driving this periodicity that we see over here. Because as soon as I get to 1, then I know it's going to repeat. This is usually called Fermat's little theorem, which is often abbreviated FLT, which confusingly also gets used to abbreviate Fermat's last theorem, which is a very different and much harder thing to prove. So Fermat's little theorem is one of these really important little results that you're going to see being used as an argument for why a ton of algorithms and cryptosystems work when we talk about them later. As I alluded to, Fermat's little theorem is definitely not true modulo numbers that aren't prime. However, there is a generalization of it that is true modulo composite numbers, and that theorem is called Euler's theorem, but we're going to put off talking about that until later. So for now, we're only going to think about Fermat's little theorem and working modulo primes and that kind of thing. When we looked mod 13, the thing we immediately knew was that the period of each element was going to divide 12, which meant the period was going to be one of 1, 2, 3, 4, 6, and 12. And as it happened, we chose two numbers, kind of at random, and we got one that was period 3 and one that was period 12. These elements where the period actually is as large as it can be, that is, when the number that divides p minus 1 that we get actually is p minus 1, we call those primitive. And I'm usually going to use the letter G to represent one of these things. And the G here is really standing for generator, which you don't really have to think about exactly why I'm thinking about it as a generator, but that is what the letter G is standing for there. And so in this case, actually, when I said the period of 2 to the x is 12, what I'm really telling you here is that 2 is primitive mod 13, or is a primitive root. So you can either say 2 is primitive or is a primitive root, whichever you want. This is explicitly a proof that 2 is primitive mod 13, because I saw that the period here was, in fact, exactly 12. Now, I'm supposed to be talking about why primes are nice and why working mod primes is nice. And this is a definition, so there's nothing really nice about a definition. Either it does apply or it doesn't. So it must come with a theorem, and it does come with a theorem. And the theorem, which still I find quite surprising, I admit, is that in fact there always is a primitive element. So here's the theorem. For every p, there always exists a primitive element modulo that prime. Again, for example, for 13, 2 is such a primitive element. And I should specify here, usually there's not just one, usually there's lots of them. So for now, if I ask you for a primitive element, what is it we have to do? Well, we basically have to try stuff. And so if I give you some new prime, you might start by trying and seeing is 2 a primitive element, and maybe it will be and maybe it won't be. If it is, great, you've found a primitive element. If not, well, then move on. Try 3, and so on. Here's a hint for you, by the way. You can convince yourself if 2 is not a primitive element and you ever get to 4, 4 is definitely not going to be a primitive element. Because if you think about what the powers of 4 are, the powers of 4 are sort of every other power of 2. And so since the powers of 4 are every other power of 2, the period of 4 to the x is always going to be at most as long as the period of 2 to the x. Anyway, so you try 2, you try 3, you remember not to try 4, then you try 5, and so on. And eventually, you find a primitive element. Again, maybe worth explicitly saying, since we're talking about algorithmic efficiency next week, if you're talking about a 100-digit prime, just knowing there exists a primitive element doesn't help you if you can't find it. And you're definitely not going to find it using the Tommy algorithm of try 2, see if it's primitive, then try 3, and so on. You're going to need to be cleverer than that, and we'll talk about that some next week when we start talking about algorithms. But for now, by hand, I'm not going to ask you to find a primitive element of anything that's larger than 2 digits, and so you can find it by trial and error. So you might ask, why do I care about there being a primitive element? And it turns out there are lots of reasons, but one reason that's especially nice is that if there's a primitive element, every non-zero element, modulo p, is equivalent to a power of that primitive element. Let me show you what I mean by that by doing this example again with here g is 2 and p is 13. Again, I'm using the fact that we already showed this video that 2 is a primitive root, mod 13. And so if I write down all of my non-zero elements, mod 13, well, all of my non-zero elements, mod 13, are going to be a power of 2. So 1 is 2 to the, and I'm going to let myself write that as 2 to the 0th. I'm going to sort of honor the fact that a non-zero thing to the 0th power is 1. Okay, saying that 2 is a power of 2 is not impressive. 3 is 2 to the, okay, and so I have to look, 3 is 2 to the 4th. 4 is 2 squared. Okay, that's also not very impressive. 5 is 2 to the 9th. 6 is 2 to the 5th. 7 is 2 to the 11th. 8 is, no surprise, 2 cubed. 9 is 2 to the 8th. 10 is 2 to the 10th. 11 is 2 to the 7th. And 12 is 2 to the 6th. So that is every non-zero element, mod 13, written in this form, that is written as a power of 2. Why is this handy? Well, if you have this chart in front of you, it makes a lot of calculations very easy. So for example, what is 8 times 9 mod 13? Well, I look and see that 8 is 2 cubed. I see that 9 is 2 to the 8th. And so now this is 2 cubed times 2 to the 8th. I have transformed this multiplication problem to an addition problem. So this is 2 to the 11th. And then I look back up, 2 to the 11th, that is 7. And so what I've done here is I've transformed a multiplication problem into an addition problem. Another example, what if I ask you for the square root of 10 mod 13? Well, the square root of 10 is, by this, it's the square root of 2 to the 10th. So, no surprise, the square root of 2 to the 10th is 2 to the 5th, just like it would work for regular numbers. And 2 to the 5th, I can look up, it is 6. And so 6 squared, you can check, is 36, which is 10 more than 26. And so 6 is really the square root of 10. Of course, there's actually 2 square roots of 10. What's the other? The other is 7, namely minus 6. So again, this difficult calculation becomes easy once I have this table laying in front of me. So what have I done here? Well, in fancy terms, what I've really done is I've written down a bijection between two sets. Namely, the set of exponents and the set of non-zero things mod 13. Or, because people like words, the set of non-zero residues mod 13. So really what I'm saying is each primitive element gives you a bijection between the set of non-zero residues, which is 1 through p minus 1, and the set of exponents, which start at 0, and actually, if you think about it, go up to p minus 2. Why p minus 2? Well, because by Fermat's little theorem, g to the p minus 1 will be 1, but that's the same thing as g to the 0, so we've already done that one. Now, if you're looking at this and you're thinking, my word, this is an off by 1 error waiting to happen, you're absolutely right. But all I'm saying here is that we have a map between these two things that lets us translate back and forth between addition and multiplication. And addition is a cheaper and easier operation than multiplication, and it expedites a lot of things, such as, for example, taking square roots, multiplying, or even finding inverses, actually. Because if I say, hey, what's 9 inverse? Well, that is asking me what is 2 to the 8th inverse. And so here's where I have to remember, this is going to be 2 to the minus 8. This exponent here is really operating mod what? This exponent is really operating mod 12. Again, that's what Fermat's little theorem says, is that actually the exponential function omits 0, and so it in fact repeats every 12 instead of repeating every 13. So I can really think of this exponent here as living a mod 12 life, so this should be 2 to the 4th, and what's 2 to the 4th? Well, it is 3. And if you check, indeed, 9 inverse is 3, because 3 times 9 is 27, which is 1 mod 13. Now, this whole idea of changing multiplication questions into addition questions is actually what logarithms were originally invented for. And so if you've ever seen a slide rule, like we have a gigantic slide rule living around in our sort of student lounge on the 3rd floor of Olin, you'll see that the purpose of a slide rule was actually to translate two numbers to their logarithms, add them, and then translate them back to the original number, basically as a way of performing large multiplications accurately before there were calculators. Much, much more efficiently than the same calculation on an abacus, for example. Now, for the mod 13 example, we answered this question by force. We just listed every power of 2 and then recorded what power of 2 matched with what element. But you might not want to list everything, and you might still want to make this translation. That is, you want to translate from the element mod p back to a power of g. Because if you already know g is a primitive element, then you know there is such a thing. So this k is called, and this is exactly the notation, again, that you would guess, the log base g of a. This is exactly what log base something means for integers or real numbers or whatever. And this is called the discrete log problem. Now, a fact that we're going to come across a number of times is that this is capital H hard. Now, when I say hard, I don't mean that there's a lot of difficult math involved. Rather, what I mean is computationally, the best known algorithms for calculating this are not terribly much better than doing what we did mod 13 to write out the table. And what that means is that even if you have a primitive element and a prime, if the prime is large, you're not going to be able to calculate these things. And in fact, a lot of cryptosystems rely in a very heavy way on the fact that you actually can't calculate discrete logarithms in a practical way. And just philosophically, I want to point out, it sounds bad when you hear that a problem is hard, but actually, cryptography completely relies on the existence of problems that are capital H hard. Because if there aren't such problems, then there's no way you can make your cryptosystem uncrackable. And so the idea is you really need to come across these things where it is easy to calculate g to a power and then hard to recover the power from seeing this. You need something where one direction is easy and the other direction is hard.